Hello everybody. Today I wanted to record a video about something I was programming the other days. And most of the time I program, I explore stuff, concepts and how they work, stuff that interests me, not real projects. And for a long time I was wondering how the print function works under the hood. Because abstraction layers are quite annoying to me because they don't explain how things work. They just explain what things do, what they do for you, what they return. But I had no idea how does our data, our string, gets from our program to the console we see here on our screen, which is another program. So I took my time and implemented the print function in Go from scratch without dependencies. And I wanted to show you what I did, how I did it, and explain some things. As you can see, I also implemented print line and printf, but they all are based on the print function and call the print function. So the thing that we want to look at today is this little function over here, which has more lines of comment than actual code. And as you can see, I have two dependencies here, time and string_conf, but they are not used inside this function, but in the printf function and in the log function. So this function has no dependencies at all. The first thing we need to know is that we have to communicate with the operating system because the operating system handles printing stuff to terminal. So at the end, what we really need to do is just call the operating system with something called a syscall, a system call. That's like an API the kernel provides for you to do useful stuff. And it provides one function that is called write. A syscall called write. And we need to use this to print stuff to our terminal. And in the Go standard library, there's a package called syscalls where the write function is implemented, but I did not want to use it. It's highly recommended that you use it because it's platform independent and my implementation is not. Because at the end, you always need to implement a syscall in assembly code in machine language. And that's why it's never platform independent. And the syscall library, as well as the standard C library, they just implement these assembler implementations for you and make your life a lot easier. But we want to explore, so we don't use it. What we will use, I'm on Linux, by the way, 64-bit architecture, which will get important. So I knew I had a syscall I need to call. But how do you know how to call a syscall and what does it need from us? Except for the string, obviously, which we want to print to the screen. So I went to the internet, Googled, and found a blog, which has a nice table with all the syscalls a Linux 64-bit architecture holds for us. And there are a lot. There are like 300, I guess. Yes, over 300 syscalls we can use. We are only interested in one today, and that's called syswrite, our write system call. It has an ID, that's the number 1. We need to pass this ID to the kernel, so the kernel knows which syscall it needs to call, to execute. It also takes one parameter called fd, which stands for file descriptor, a concept we will look at shortly. The second argument is our string. Um, it's marked here as constant char pointer, like you would write it in C, which is a string, a non-mutable string. And the last argument is the count. Count means count of bytes we want to print to our screen. One character inside of a string, and C has always 1 byte. So it would also mean the number of characters. Yes, exactly. So we need those 3 arguments. But first, let's have a look at a wonderful flowchart Gemini has created for me. So we have our Go program. And there's a concept called file descriptor, which is a number, basically. There's the one that stands for standard output. Standard output is something linked to our process, to our program, where we always write to when we call the print function, or in other languages the console write whatever functions. It always goes to standard output. A lot of times we can provide other destinations where we want to write, but if you don't provide anything, you will always write to standard output. And there's a table inside your process description, probably, where you have like the number and then a pointer to something where standard output lives. And this something is called TTY, or sometimes I guess PTY. TTY stands for telegraph typewriter, I think. And I have no idea what PTY stands for. But as far as I understood it, it's a buffer inside our kernel where we can write data to, and other processes like our terminal, our console, reads from. And this is a ring buffer, so a circular array. Exactly. And we will have a quick look at a table of file descriptors. It looks like this, I assume. Found that on the internet. I have no idea what session and job stand for, but I know that every process has a stream for standard input, standard output, and standard error, where you can send error messages to. And our file descriptor points for standard output, it's the number 1, points to something, our TTY. And that's, as I understood, is a ring buffer. A ring buffer, a circular array, is an array which has basically no ending. It just means that when you reach the end and write the next item, you will start at the front again. And so that's why you draw it like a circle. And a lot of circular buffers have 2 pointers, a tail and a head. Tail is the index in the array where we can write next, which is 3. And the head is where we want to read from. And in our case of a TTY or PTY, this would mean that our standard output file descriptor points to exactly this tail, where we can write data. And our terminal would have a pointer to the head of the circular buffer, where it can read from. And obviously the head cannot overtake the tail, because we cannot write what was not written before. But yes, that's essentially how your data gets to your terminal. I actually have no idea how the terminal knows when to read. If it just like loops and looks if there's new data or if there's a callback, and the operating system wakes up the terminal and say, hey, it's data here, go get it. Probably because that's more resource efficient. That's the word I was using, was searching. And yes, so we have a rough understanding how our data flows from our program to our console. This stuff we don't need to implement. That's inside the kernel of the operating system. We cannot touch it. We cannot, I want to say speak with it, but that's not right. Communicate with it. Please have some patience with my English. So we just use an interface called system calls, where we need to store the data inside some CPU registers. That's why we need to use assembly. Then interrupt the kernel with the syscall signal, and then the kernel will fetch the data from the registers we put our data in and does this stuff exactly. And then we will see the text at the terminal. Wonderful. Yes, here in our blog post we can see that the registers are specified. The ID of the syscall, for example, needs to be in the AX register. There's where the CPU the kernel will look for the ID. When we store it in a different register, it won't work. Same goes for our file descriptor, also a number passed in the DY register, which are, by the way, in a 60-bit architecture, 8 bytes of size. The SI register will hold our string, not exactly our string because that will be more than 8 bytes, but it holds a pointer, which is 8 bytes, to our string. So a pointer to the memory location in our RAM where we put our string in, or the compiler put our string in. And the size is also 8 bytes in the DX register. Maybe those registers are a bit longer. I would say they are 8 byte, but it's not that important for us. So we need to write an assembly file where we store one number in the AX register, another number in the DY register, a pointer in the SI register, and a third number in the DX register, and then perform syscall. So let's have a look at our code for that. So we can see we provide string as an argument for our print function. Then we call something a function, syswrite. And we provide a number, 1, and a string. This number stands for the file descriptor 1, not the ID of the syscall, actually. Then this function will return the count of bytes that were written to the terminal, because the OS cannot guarantee us that our string will be written in its whole, because there can be other interrupts that are more important than us writing something to the console. That's why we need to check for this n, which I don't do, but we should do it. We should check if this number of bytes written is the same as the size of our string. And if it's not, we just need to call the syscall again, where we need to pass the bytes that were not written yet to the screen. I just check if this number is 0 or greater, because if it's negative, we cannot write a negative number of bytes to our console, obviously. This means we have an error. And then I log it and say, hey, there was something wrong. as far as I know, there are different negative numbers for different types of errors, which the kernel provides us, but I have no idea what they are, so I didn't check for it yet. Also, if your string is like a normal string size, it almost every time gets printed as a whole. They are like, if you print a whole file, which is very long, a lot of characters, then it could happen that it gets interrupted. Okay, as you can see, there's a function. I said we have no dependency, so where is this function? This function is declared here. Function syswrite takes a file descriptor, which is an integer, and string s, and returns an integer. But there's no body. There's no implementation of this function. This is because, as I said, we need to implement this in assembly code. And Go has a, I think, very good way of providing the opportunity to implement assembly code in your Go program, which is have another file, and there your assembly goes, and it just needs a label with the exactly same name as this function declaration, because your compiler will look for it. And it also needs to have the suffix underscore AMD64, because that tells the compiler, hey, this is for 64-bit architecture, AMD and Intel chips. If you have a 32-bit operating system, for some reason, then the compiler will not execute this code, because it knows it won't work. So let's have a quick check. How does this assembly code looks? If you've never seen assembly before, it looks quite complicated, but actually is not that harsh once you have seen it a couple of times and get used to it. It's quite normal that it takes some time, but I will explain every step we do, and I hope this will help. First of all, we have a label, syswrite. This label was generated by AI for me because it's a dialect of assembly I've never written before. I have no idea what does SB stands for, or no split. There's some explanation that no split means we don't need dynamic stack memory, but I have no idea what dynamic stack memory is, so yeah, I just don't know. Not too important though, because it works. The last number is more important for us. The 0 means 0 bytes local memory. I again don't know what this means, but the 32 bytes are the size of our stack that our program holds. Inside the RAM, or the stack on the RAM, every process has its own stack frame, and every function will get, I don't think every process has its own stack frame. I think that's wrong, but every function does have it. That's why we have a scope, a variable scope. A variable you declare inside of a function. You cannot read, sign, do anything with it, see it outside of your function. That's called scope, and that's because it lives on its own stack, in its own memory, and it doesn't know anything else. We need 8 bytes for our integer that we will pass into this function. We need 16 bytes for our string, because a string in Go is always, independent of its size, 16 bytes of length. I will explain why in a moment. And we have a return value of 8 bytes. 8 plus 16 plus 8 is 32. So our stack frame needs to be 32 bytes of size. Why is a string in Go 16 bytes of size? Well, it's quite simple. There's 8 bytes. The first 8 bytes of a string is a pointer to the memory address where the actual data of the string is, or more likely a pointer to the first character of our string. the next 8 bytes is the size of our string as an unsigned integer. I would suggest of 8 bytes. Yeah, obviously, it's 8 bytes. So we know where lives our string and how big is it. That's perfect because we need to pass, as you remember, a pointer to our string, to the syscall of the kernel, and the size. And we have both inside of the string. That's why we only have 2 arguments in our Go code. So let's step into the assembly code. Assembly is always some instruction like move q, which stands for move quad, I think, because it's a 64-bit operation. It moves stuff. And then there are 2 arguments. The first is what do we want to move, and the second is where do we want to move it. So FP stands for frame pointer, I think. That's the pointer to our stack frame. And then we provide an offset of 0 bytes, which means, hey, start at the beginning of our stack frame. The next 8 bytes, we call it FD and put it into the register DI. Normally, in assembly, you would not need to provide a name for it, but it helps our Go compiler to map these names to our arguments we pass and perform things like type checking and stuff. It just helps you. So Go actually forces you, the compiler forces you, as far as I know, to provide a name. Okay, so we move the first 8 bytes of our stack frame where we put our file descriptor into the DI register because, as we remember, sorry for the brightness, that's where we need to put our file descriptor. So we do it. The second instruction is to move something called sData, string data, from the frame pointer to the SI register. That's the pointer to our data to our string, which has an offset of +8 because we start at the beginning of the frame pointer again, of the stack. And then we say, okay, but we have an offset of 8 bytes now because the first 8 bytes, there's the FD argument. The second 8 bytes is the pointer to our string data. We put that into SI, and the third 8 bytes, so we have an offset of 16 bytes now, is the length of our string, and we put that into the DX register. So nearly everything is set up now. The only thing left we haven't configured yet is we need to put into the AX register the ID of our syscall we want to perform. In our case, 1, because we want to perform the write syscall. If you want to move an actual value into a register instead of like a variable that holds a value, we need to prefix it with a $sign. So after that, everything is set up now, and we just write one word, syscall. That's an interrupt. The kernel will switch its context, do stuff that I explained, put our data, looks where the file descriptor points to, puts our data in that circular buffer of our BTY, probably calls our terminal, which wakes up, takes the data out, and is happy and prints it to our console. And then the kernel puts the result, so the number of bytes that were written, back into the AX register. In assembly, you cannot decide where your return values land. They just land somewhere, which is specified, obviously, which is most of the time some register like A. If you add 2 registers together, for example, I think always the first register where the return value, the result, lays. So we want to access this value in our Go program, so we have to put it back on our stack frame. But we need to put it at the free space we have. So we have an offset of 24 bytes now. We call it ret for return. And yeah, move the value inside of AX, inside of this register, onto the stack frame. And then we just return to our Go program. And then we land here. N is now the value that lays on the stack frame at offset 24 bytes. And then we just check, is it negative? No, perfect. Everything works. And I have to have a quick look here. Yes, there's still stuff inside of our main function. Okay, we just call our print function now with hello world. Save this. And then we just need go run main go, which probably won't work because we need to compile print go also. And if we run this command, we see hello world. So we printed text to the console, which is quite cool, I think, because I always wondered how does this work, and now I know. And I hope you know now as well. So what did we do? Let's recap. If I find my flow chat. Perfect. We implemented print and saw how our code passes a string through a system call to the kernel of the operating system, which knows where our standard output lives, puts our data inside of the standard output stream, and then it gets written by another process which is not part of the kernel of the operating system, just in terminal. Just a program like this. And yeah, prints our text to the console. So thank you for your attention. I hope you found this informative. And I hope you had some fun. Maybe try to implement it yourself, or try to implement other functions with it, like there's a read function. We can input stuff here, press enter in our program and catch this as an input and read this. You can implement it almost the same way as print, again within system call. So have fun exploring and doing stuff. Leave feedback in the comments if you have some. And yes, thank you for listening.